on your homework, stuff like that. Okay, so we're looking at this golf hole that I designed, right, as if I were doing the project that you guys are about to do. And previously, we had found angles 1 and 2, and kind of our rationale behind that was you guys had to prove to me that you are designing your golf hole and that a hole-in-one actually is possible using the physical principle that a ball hits a wall at one angle and bounces off at that same angle. So for me, proof was for you to draw your scale model and then measuring only by a ruler and doing calculations, show me that angle 1, when I calculate it, comes out to be the same as angle 2. Okay? And we did that by enclosing those angles in triangles, measuring some things around them and using tricks. So we had done these calculations to find, sorry, it's a little slow today, to find these two angles, and we came up with the fact that angle 1 and angle 2 got these measurements, and that some people might feel like that means they're not equal, and you're right, technically they aren't exactly equal, but we talked about the fact that we are drawing this on graph paper, we are going to be using a tool, we are doing the measuring, and so I am allotting you guys a little bit of graciousness, some human error. We said within 4 degrees that I'll still consider the angles equal, and that will be enough proof to me that you designed it using the principle that we talked about. Okay, so do you guys remember generally, like, that's what we talked about? So goal today, the angles that we didn't get to, the ball hits the wall again right here. Okay, so the ball's hitting the golf hole, it hits the wall there, ricochets, hits the wall here, ricochets into the hole. That's how this hole is supposed to work if we're going to get a hole-in-one. When you guys are designing your golf holes, just be aware, my minimum requirement is going to be 2 ricochets, and like one of the things can't be parallel and perpendicular. You'll see all those things. Notice I did 2. If you design your golf hole and is like, this is going to be so cool, mine's going to ricochet 10 times, that's awesome. Let it ricochet 10 times, but you have to prove to me that every time the ball hit something, it followed this principle. So because I have 2 ricochets, we have to do the work of proving 2 angles congruent twice. If you put 10 ricochets into your golf project, you will be proving pairs of angles equal 10 different times. Does that make sense to everybody? So be smart about your project design, okay? I'm trying to tell you how to cheat the system, all right? So do it the right way. All right, so the reason we couldn't find these angles last time is when we take angle 3 and angle 4, because they had to ricochet off of something that's not parallel to the grid lines on here, when we connect the path of the ball and the wall this time, here's my line connecting them, it doesn't make a right triangle. It makes a different triangle. So do you guys understand why we had to wait till we acquired these 2 new law of sines and law of cosine tools before we could come and prove that angle 3 and angle 4 were equal, okay? And then I'm gonna do this quickly because I don't think you guys are gonna go home and like practice this today or anything. I just wanna make sure that you have the example of it and the idea behind it. And then you guys will get more time to talk and form groups and talk about your project, okay? So here are some really rough and not so cute sketches of the angles that we found. Oh, they're having a lot more fun. Sorry, guys. Okay. All right, so angle 3 right here, right? These were the sides surrounding it, and these numbers that you see came straight off of what was measured on the paper, and that's what you'll do. You'll literally measure it on your paper with a ruler. So this was 1 inch, this was 3 inches, this was 3.375 inches. Okay, so those are where I'm getting these numbers that are surrounding angle 3. Is everybody okay with that? I formed a triangle, I measured those things with a ruler, I drew a little sketch of what was happening over here. Then I decided to call it A instead of 3 because it's really confusing to me to have an angle called 3 in an equation that I'm trying to solve with numbers, so I would rather give it a letter name to understand it's a missing piece of information, okay? Who can tell me why I could not use SOHCAHTOA to find your trig ratios, angle 3? Minami? Good. There's no guarantee this is a right triangle from our picture. We didn't have things connecting on the grid lines that were parallel to one grid line and parallel to the other that guaranteed us a perpendicular right angle. We don't have that here. So when I don't have that, I can't rely on the tools that use the hypotenuse, something in a right triangle, to solve. So we're going to use law of cosines. Who can tell me why I can't use law of sines here? Because I like it. It's much simpler. Why can't I use law of sines to solve this triangle? I see Minami, but she answered the last one for you guys. Or? Good. In the law of sines, we want ratios where we have an angle and the side across from it. We don't have any angles in this diagram, which means if I try to take the sine of an angle over something and set it equal to the sine of a different angle, both of the angles in the equation will be missing, and I can't solve it, okay? So I'm stuck using law of cosines in this instance, okay? So when you set up your law of cosines equation, mine's already set up. I'm just going to talk about where I got the numbers. So I'm going to zoom in and I'll zoom back out if you're struggling with where they came from. First of all, the angle right here. I needed to use the angle that I'm finding, and I know this wasn't labeled, so you have two options. Number one, thoroughly go through and label your triangle. If you called that angle A, go call the other ones B and C and mark the appropriate sides, and then you can use the formula just like you have on worksheets, okay? Second thing, look at the three versions of the law of cosines, okay? In each of the three versions, whatever angle you're using, the side across from it, like when I'm using big A, little a is on the other side of the equation by itself, right? So if I'm using angle A, 3 got over here put on the other side of the equation by itself because it is the side that is across from the angle I'm trying to find. Then the other two sides got plugged into the other spots in the equation, okay? And remember, you guys, I'm not requiring you to memorize the equation, but you do then have to put some effort into being able to fluently use the equation, even though you don't have to memorize it. And then I'm just going to mark a couple things so you can see. The next thing I did is I combined together these things. Okay. Do you guys remember why we can't combine them with the other number here? I multiplied these out, but I kept them separate as the 6.75. That 6.75 is multiplying a cosine. The other values are not. So you can't just combine the 6.75 with the 12.3906 or okay? And then I worked on solving this equation. So first I want to cancel this out. So I subtracted the 12 here and on the other side. So that gave me this line here, this negative 3.3 equals this times the cosine. And then I wanted to cancel this out, so I divided by negative 6.75. Okay? And then remember, the final step in this is to use inverse cosine in order to solve for A, and we get 59.8. All right, so what you should be asking yourself is, do you understand the difference between what I'm calling classwork 4, this problem we're working on right now, and what we called classwork 3, the problem you worked on before? Your goal is the same, to find two angles using triangles and prove that they're equal. But in classwork 3, we got to use our SOHCAHTOA ratios. Here, we're forced to use something different. So step 1, are you going to understand your project when you get to use your sine, cosine, tangent ratios and when you can't? Okay, like here, we don't have right angles. Then step 2, same thing we talked about in our notes on Wednesday. When we're using these, since we don't have to memorize them, it's really more like, do I know when to use them? Do I know how to plug things into them? And then do I know how to solve? So are you guys okay with what I plugged in where? Is the first question. And then the second question is, are you okay with my steps for solving? So think about it for a second. Are there any questions on either of those things? Do I know why she put the numbers where she put them? Do I know how she did each step to get A alone at the end? Anything? No? No? Right, so we would apply the same idea to find angle 4. I didn't write out all the work for angle 4. I just put the setup and like what the answer is. Again, because our emphasis here is not on how to do it. That was in our notes and our homework. The emphasis here is just like, how does my mini golf project relate to what we're doing? Okay, so for triangle 4, I'm going to scroll back, but I'm going to bring this back in a second for those of you freaking out. So this is the triangle I'm focused on. See where angle 4 is? See the yellow highlighting around angle 4? And the things I highlighted were the wall, the path of the ball, because that's how angle 4 is made, between the wall that's hitting and the path of the ball leaving. And then I connected them with that dashed line. Okay, so those are my measurements for angle 4. And then here's just a really rough sketch then of what those things look like, so I can see it as a triangle with measurements around it. Just repeating what I did with 3. So I just highlighted the two things that made angle 4 and connected them to make a triangle. And then I measured those distances with a ruler on my paper to build kind of this generic problem like we might see on a worksheet. And then the setup idea would be the same. If we're trying to find this angle right here, it's going to have to be in our equation, and the side across from it is 3.125. So when you go to use that law of cosines formula, if you want to see this angle in your equation, you want to see the 3.125 as the number on the other side of it. And then the other side lengths can fill in these values here. Okay. When you solve this equation, we get that angle B is equal to 56.2. And this one pushed our limits on what we said okay. You might look at that and be like, Ms. Dahl, those are not the same, but what is the amount of degrees that I'm giving you to be accurate? 4 degrees, okay? So what we have there, 3.6, just cut it, okay? And before you guys go, if you're doing the project and you're like, oh, I didn't get within 4 degrees, before you go crazy and are like, I have to do the whole thing over, just go remeasure a couple of things. A very small decimal might change the amount of degrees between, or if it's a right triangle, instead of doing sine, try using tangent and 2 of the other sides you measured, and you might see that like that one seems a little more accurate, and that might save you a lot of extra work, okay? Is everybody okay with the idea that when you do your design, every time the ball bounces, you're going to be proving 2 angles equal? The way you're going to prove that equal is by making triangles and using some of your solving triangle skills to find the angles. Okay? And you don't have to find everything else. You just got to prove to me those 2 angles are equal. So in each triangle, you're just trying to find one of the angles, okay? Specifically the one where it ricochets off the wall. All right, the last 2 things that are going to be included in the calculations for your whole design are on the back. They're called classwork 5 and classwork 6 on there. These are actually not really anything to do with solving triangles, just more to do with scale. And scale is actually a really good real life application type of thing. I used it the other day when we were designing my backyard. If you talk to Miss Harper, every time she designs where furniture is going in her house, she has a little scale model on graph paper and little movable pieces so she can see how it fits in her stuff. So you actually can use it. So the other things are about scale because they're appropriate for you to actually build your golf hole accurately on the day we do get to walk around and golf some of the golf holes. And so there's 2 things I'm going to ask of you in the project, and I just want to review them quickly because I want to make sure you don't do the scale wrong for something that's a smaller calculation. So thing number 1 is going to be that your golf hole is going to have to be designed that it fits in a 32 square foot area. So the reason 32 square feet is that's big enough to actually play the golf hole, but small enough that we could fit 2 or 3 of them inside the classroom and 2 or 3 of them inside the hallway. Okay, so I kind of put that. If you're building your own at home, which we'll talk about in a little bit, and you're like, Miss Dahl, I need a little more than 32 square feet. I had a kid build a 2-level one time. Like, oh, it starts up here, it goes down there, takes up more than 32 square feet. Just come talk to me. We can accommodate, because if you're going to go out of your way and build something awesome like that, clearly I don't want to stop you. I want to encourage it. So when you're finding the area, we want the real life area. Okay, look down at the floor in our classroom. The tiles on the floor are 1 foot by 1 foot. Okay, so that's 1 square foot is the tile. Okay, is it good for me to build a mini golf hole that is 4 square feet for you guys to play? That would be like these 4 tiles together. It would be pretty difficult for you guys to play golf. I don't know, unless you're going to make like a miniature version of anything. I don't know. You guys come up with some crazy ideas. But in general, if we're using the supplies, that's not going to work that well, okay? So you want to design a golf hole within 32 square feet. Close to 32 is pretty good. Those are a nice playable size. And then let me show, I see you guys are copying down, but let me show you how I did this. First of all, be smart. You're designing it, right? Like, do you want 10 ricochets in your design to go do the calculations we just did 10 different times? Like, I don't think so. Be smart with area as well. Look at how I designed my golf hole. The shape is not difficult, right? Okay, I can put crazy things in there, but the general shape is simple for me to find the area of. And notice that when I outlined it on the graph paper, I didn't like stop it at some random place. I really tried to use a distinct number of graphing squares. And then I made my scale purposefully like this 3 inches here. Every square on the graph paper is 3 inches in real life, okay? So that means on here, when I look at this distance right here, and I see that that's 1, 2, 3, 4, 5, 6, 7, 8 graph paper squares, okay? I can tell you how much that is on paper. On paper, it's 8 times 0.25 because every square is 0.25 inches on paper. But in real life, these squares are supposed to represent 3 real life inches, okay? So 8 squares on paper means 24 inches in real life, and I convert it to feet because the limitations are given to me in square feet, okay? So all I'm going to do to calculate the area of my overall golf hole is, number one, understand the overall shape of my golf hole, which is like this L. Okay. Then I'm going to think about how do I find area of an L. There is no formula for area of an L, but I can pretty simply, split it into two rectangles and find the area of each of the rectangles. Okay, and then for each rectangle, I went and I counted the graph paper squares on my paper and said 8 graph paper squares means 24 real life inches, and 24 real life inches is 2 feet. Okay, then I did it for the other dimension right here. It ended up being 30 real life inches, which is 2.5 feet, and 2.5 times 2 makes 5 feet squared for the area of that rectangle. Is that okay with everybody where we're getting these numbers from? Any questions on how I'm getting the numbers, the inches or the feet? Okay, so I did the same thing for the dimensions of this rectangle up here. The area of that larger rectangle ended up being 24.5 feet squared. So the total area of my golf hole is this 5 square feet from that, plus that 24.5 square feet, which gives me 29.5 square feet. Okay, so is it within the requirement of 32 square feet? Yes. Is it golfable? 29.5 of these squares that sit on the floor in front of us, would that be a feasible region to set up a small little mini golf hole? That would work okay. All right. So I know looking at the floor is kind of silly, but it does help you figure out like how large things actually are. The last thing you have to do is you have to know how far the golf ball travels. So I'm going to ask you guys, when you build your golf hole for us to play, that you outline the theoretical hole-in-one path. So when people come look at it, they say, oh, that's how they say I can get a hole-in-one. They can try it or not try it, up to them. So you're going to have to know how much tape you're going to need to lay on the floor to outline the path of the mini golf ball. Okay, so when I look back at my sketch and where the golf ball went, here was the beginning, here's the end. The golf ball went along here, then here, then here. That's the path the golf ball traveled. Is that okay with everyone? So all I have to do is measure those on the paper with a ruler and add them all together. So they've already been measured for you and marked down there. And so here they are being added together right here. Okay. And they make a total of 12.5625 inches, but that is on paper. If you come to me and ask for 12 inches of tape, that's going to be like this big. That's not going to outline on your real life golf hole how much the path of the ball. You're going to need a lot more tape than that. So we have to do a unit conversion like you guys would do in science, okay? Not to change it from inches, but to change like the inches on the paper to the real life inches. So just a little bit of review of how to do that. This is the important part, is that you recognize that that 12 inches is on paper. And remember, anytime you want to change the units of anything, you can multiply by a fraction that will cancel out the units you want to cancel and leave you with the units that you want. So the way I set up this fraction is I knew I wanted to cancel out the words on paper because I didn't want the measurement on paper. And I wanted to end up with real life. So I put paper down here so that it would cancel out that word paper. And I put real life up here so that it would leave me with real life as my measurement. I'm only allowed to use this then if I have amounts that are equal to each other. So really this is worth 1 because the amount that's up here is equal to the amount up here. They're just being measured in different ways. So on our scale, it said that every little chunk of the graph paper, on paper it was 0.25 inches, but in real life we were calling that 3 inches. So is everybody okay with why I set this up? So this helps me know what I want to set up to cancel out, and then I put the numbers in based on the scale I was using. So I took that 12.5625, multiplied it by 3, divided by 0.25, and got 150.75 inches, which makes a lot more sense if we built that bigger golf hole, that we would need that many inches to outline all the ricochets of the ball. Okay? Is this okay with everybody? All right, so this is the work you're going to be doing.